All our lives, we're pulled about and pushed around by the mysterious workings of chance. When chance seems cruel, some call it fate. And when chance is kind, we might call it luck. Scoring a big win, being saved from disaster, or meeting that special someone. But what actually is chance? Is it something fundamental in the fabric of the universe? Does chance have rules? And does it really exist at all? And if it does, could we one day even overcome it? This is the story of how we discovered how chance works, learned to tame it, and even to work out the odds for the future. How we tried, but so often failed, to conquer it. And may finally be learning to love it. Chance plays its part in all our lives, though mine perhaps more than most. I'm a mathematician at Cambridge University, and trying to make sense of chance is my job. I study how we can use the mathematics of chance to calculate probabilities, numbers that can give us a handle on what might happen in the future. Did you know that on average, each person in Britain has a 1 in a million daily chance of some kind of violent or accidental death? To put it in perspective, 1 in a million is roughly the chance of flipping heads 20 times. Heads? Imagine it like this. Flip a coin, 20 heads, you're dead. Heads? Heads? Oh dear. Heads? Tails. A few. It's easy to say that it's 50-50 for a coin to come up heads. But we can even put a probability on things that seem utterly chaotic and unpredictable. San Francisco. In October 1989, a huge magnitude 7 earthquake struck totally without warning. Many people died. Today, San Francisco is its usual laid-back and beautiful self. But the people here know another disaster could hit at any moment.
I know that my family members, we all have the earthquake kits and we try to have things ready. But other than that, we're not very fazed by it, I don't think. Not until the big one comes.
I believe in being prepared, but I also believe that it is fate.
I've been here for over 20 years, and it kind of puts you in a place where you live a little bit more in the moment, where, you know, as much as you prepare, there's something can hit at any time.
For millennia, we've met the uncertainties of life with just a fateful shrug of the shoulders. But mathematics can help us quantify fate, even if we can't banish it.
What we now know from our studies is that the likelihood of a major earthquake hitting the Bay Area is something like 63% over the next 30 years. But associated with this 63% number, which sounds very precise, there's actually a huge range of uncertainty. It could be mid 40% or it could be 80%.
Probabilities are often as much a matter of judgment as arithmetic, but they can still really help people decide what to do.
After the 1989 earthquake, there were a lot of aftershocks, and a woman called me and she said, "I'm so nervous to be here. I think I want to drive to Los Angeles to visit my daughter." And I said, I don't think that's a good idea. And she said, why? I said, well, the likelihood that you'll be injured in an automobile accident is much higher than the likelihood that an aftershock will harm you.
There's no escaping chance. But if we can understand how it works, then perhaps we can even turn it to our advantage. This was what the first mathematicians to investigate it hoped to do. To, as it were, tame chance. The scholars of the ancient world, the Egyptians, Babylonians, Greeks and others, laid down the foundations for geometry, algebra, number theory and so much more. But extraordinarily, they never even got started on the maths of chance. It wasn't until the Renaissance that a few pioneering thinkers first got to grips with probability. But unlike the ancients, they weren't loftily pursuing knowledge for its own sake. They were trying to crack the secrets of gambling. The first was Gerolamo Cardano from the Italian city of Milan. Cardano was a doctor, but he was also an obsessive, lifelong gambler. This was written in the 1570s, the earliest known work on probability. In it, Cardano set out a seasoned gambler's tips and insights, including how to cheat, and in one chapter, laid out the most fundamental principle of probability. Cardano realized a probability was also a fraction. So with the roll of a dice, the probability for each side coming up was 1/6. And it gets more interesting with 2 dice. With 2 dice and 36 possible combinations, there's only one way to throw a 2. But you're much more likely to get a 7. Cardano's insight works with games like dice because we can assume that each of the faces is equally likely, provided, as Cardano puts it in his book, the dice are honest. This may seem simple to us now, but it was the very first step in working out how to tame chance. Las Vegas, a place Cardano would have surely loved. The people who run this city have the measure of chance so well, they've built an entire glittering industry out of it. It's vital, even so, that anyone here can get lucky. You could even bet $1 and win $1 million. Mike Shackelford is a professional gambler. His living depends on his command of casino maths.
I analyze every casino game out there, and my goal is to find out the probability of every possible event in every game. Almost always the odds are going to be in the casino's favor. For example, in roulette, the house advantage is 5.26% under American rules. That means that for every dollar the player bets, on average, he can expect to lose 5.26 cents.
Not only do the casinos understand the probabilities perfectly, they also know that most of the punters don't. And these games can really mess with our minds.
You'll see a series of outcomes from a slot machine and believe that there is a pattern to what you've just seen, but that's really just the human brain playing a trick on you, because what's happened in the past has no predictive value for what is going to happen next. Yes, the machine may have had this series of payouts in the past. It may have been hot or cold, but that has no bearing or no influence on what is going to happen on that next game. So you could hit the jackpot symbol 2 games in a row.
We just hit the biggest jackpot we've ever hit here. $8,600. We just went to this machine about a half an hour ago, so we got lucky.
Jackpots don't worry the casinos. They know the slots are programmed to deliver high house edges in the long run. Smart players like Mike rarely touch them.
A professional gambler plays games where the odds are in their favor. Probably the most well-known is card counting and blackjack.
In blackjack, every time a card is dealt, the odds change for all the cards that are left. Mike tracks the cards that are dealt to work out how those odds are changing.
So if the player notices that in the first 25% of the shoe, a lot of small cards came out more than expected, he knows that the remaining cards are going to have a surplus of big cards. So he will adjust his bet size and he will change how he plays. And by doing that, he can get the odds in his favor.
On a good day, Mike can get a 1% advantage over the house. It doesn't sound much, but it could mean a lot of money. The casinos, of course, don't like card counters, and Mike's been banned from almost every joint in town. In the world of games, if you know the rules, you can figure out the probabilities. But what about the chances of life and death itself? To be able to put probabilities on our own lives needed another great mathematical leap. And this time, the rewards would be even bigger. For most of history, it was almost a given that we had not the slightest inkling of when our time on Earth was up. Death visited when he wanted, and the results were never pretty. Thank goodness for the consolation of eternal life in the hereafter. The sculptors who carved this terrifying monument were capturing the brutal truth of our mortality as a warning to everyone here quaking in the pews. But around the time this was carved, about 300 years ago, scientists began trying to work out the mathematical chances for each individual that death would soon be paying them a call. The revelation was that you could study one group of people, the residents of this parish, for instance, and see how old they were when they died. From this, you could estimate the chances of death at each age for everybody else too. This was a radical idea. Count the dead, and death would become less of a divine punishment and more of a predictable force of nature. The man who really cracked how to apply the maths of chance to human lives was Edmund Halley, the famous astronomer. Edmund Halley had no interest in what went on in there. What fascinated him was what happened out here. Most people now remember him for his famous comet, but I salute him as one of history's greatest nerds. Halley realized that he could calculate the probabilities of life and death. All he needed was some good data. 83, 52, 27. In faraway Breslau, now a city in Poland, locals were spooked by an ancient superstition that being aged 49 or 63 was particularly risky. To prove the superstition wrong, a Breslau clergyman collected details of all the town's deaths and circulated these to the leading scientists of the day. Halley got hold of the data and realized the results would have an impact far beyond Breslau.
Halley constructed a table that was made up of essentially two columns. The first column was age, and the second column was how many people were alive at that age. The first column started at birth with 1,000 people, and as the ages increased, what we saw is that the number of people alive decreased. And this wasn't uniformly.
Halley found nothing special about 49 or 63. But his data showed that the older you got, the greater the chance of you dying. It seems obvious to us now, but before Halley, people thought the chances much the same for everyone, young and old alike. And Halley's table had an immediate practical benefit.
Halley's tables were also groundbreaking because not only did he publish the probability of death at a certain age, he took that one step further and applied that to the price of a pension or the price of life assurance. He included formulae as to how you could actually come up with a price for a pension.
People in the 17th century wanted to buy pensions and life insurance just like they do today. But before Halley, anybody who provided them was in danger of going bankrupt.
So Halley's breakthrough would form the foundation for the entire pensions and life insurance industry, and death would never seem as capricious and mysterious again.
And what of Edmund Halley? He lived all the way to 86, off his own table. Costly if you were his pension provider. Today, the insurance and pensions industry is huge and has collected so much data they can correlate your life and death chances, your gender, your address, your job and your lifestyle. And knowledge of the odds could help us all.
So what do we know about what affects our chances, for better or for worse? Imagine this 100 meters is 100 years of possible life. How many of those years are we actually going to see? How far along this track are we going to get?
When I was born, the average British male expected a much shorter life than if born today.
I was born in the 1950s, and back then, my expected lifespan was just 67 years. But thanks to medical advances and changes to the way we live and work, our chances are continually getting better.
The average lifespan is actually rising by 3 months a year.
If I were born today, I could expect to live to 78. Even better, the longer you live, the longer you can expect to live because you've been lucky enough not to die young. So at my age now, I can expect to live not to 67 or 78, but 82. But what's not so cheerful is the effect of all those things I might do throughout my life that could stop me getting this far, or even further.
Research tells us that for every day you're 5 kilos overweight, like I am, you can expect to lose half an hour off your life. Sad to say, if you're a man sinking 3 pints a day, then that's also half an hour. But what about exercise? Won't that make things better? Yes, it will. But there's a catch. A regular run of half an hour, and you can expect to live longer. Half an hour longer. So I hope you actually like running, because that's how you just spent your extra half hour. Surprise, surprise, the worst news is for all you smokers. 2 cigarettes cost half an hour. But the average smoker's on nearly 20 a day. And it all adds up.
Doing something that costs half an hour a day, well, that's more than a week off each year. And in the long run, that's a whole year off your life. For that 20-a-day smoker, that's a staggering 10 years you should expect to lose.
All these figures tell us a lot. But as for chance itself, that's certainly not disappeared.
When I say I can expect to live to 82, I'm not actually making a prediction. It may be shorter, or with luck it may be longer. 82 is the average. Imagine 100 possible future me's, each equally likely. I'm 58 now, and as the years roll by, in more and more of these possible futures, I die. Until, by the age of 82, about half of my future selves will be dead and about half still alive. Which is going to be me? That's just chance.
Beyond 82, more and more drop dead. And there's a very small chance I could live to be very old indeed. If I were a smoker, it's just possible I'd beat the odds. But overall, my chances wouldn't look nearly so good. Of course, many people would say going on about risks is being a big killjoy. The writer Kingsley Amis famously said, "No pleasure is worth giving up for the sake of 2 more years in a geriatric home at Weston-super-Mare." But I believe understanding the risks might actually help us to have more fun, not less.
Okay, just got one arm through there for me, other through there, and turn around. Thank you. What we'll do is we'll start strapping you in.
Many of my favourite experiences would be impossible without taking some risk. But I'm about to do something I've never done before, which really does involve risk.
The best way to compare risky activities is to use the micromort, a cheery little unit which represents a 1 in a million chance of death.
Skydiving is actually safer than you might think. There's about a 7 in a million chance of dying. That's 7 micromorts. That's about the same risk as 40 miles on a motorbike. But there's still a risk, and you may think I should be old enough to know better. But I think it could be rational to take more risks when you get older.
An average 18-year-old has a chance of dying in the next 12 months of about 500 micromorts. But at my age, the equivalent is 7,000 micromorts.
7,000 micromorts doesn't sound great, does it? But the extra risk of skydiving is only 7 micromorts more. That's not much difference.
So the risk is actually pretty low. But the funny thing is, now I'm actually in the plane and there's no backing out, it suddenly seems a lot worse.
Will my parachute fail? I don't know. Will we be blown into a tree? I don't know. Will I be sick with fright over my jumpsuit? The probability of that is getting close to 100%.
It's the moment of truth. Yes, I'm a professor of risk, and I've made a sound decision rooted in the numbers. But as I fall, I can't help thinking, there's a chance I'll die very soon indeed.
I could buy myself a pair of silver hairbrushes. Or, oh, hello, I'm having a go at these premium bonds. They're wonderful things you can't lose. Look, there are staggering prizes each month. You can get your money back anytime you like. And what's more, all your tickets go back into each drawer, whether you've been lucky before or not. I might win 1,000 quid. I'd love a bit of a flutter. Not a word to Bessie about that.
In 1956, Britain introduced a brand new kind of savings scheme, premium bonds, that instead of paying you interest, gave you the chance to win big prizes. At its heart was something created by mathematicians, a world of pure chance, randomness. This is a world where every element is disconnected from every other, that operates beyond our influence or control. The Premium Bonds monthly prize draw needed complete randomness to make sure it was scrupulously fair.
There was quite a lot of human interest in randomness for the first time, where people began to think about what are the chances of my winning. But what it required was a source of random numbers, and a special purpose computer was built for this, and it was one of the very first special purpose computers.
We're going to an electronic machine, if you understand what that is, but thank goodness its complicated name is ERNIE for short.
ERNIE stood for Electronic Random Number Indicating Equipment. Truly random numbers are hard to produce, and ERNIE got them by sampling the electrical noise from a series of vacuum tubes. It was state-of-the-art engineering.
Randomness really, in a certain extent, means unpredictable, but also, for the purposes of ERNIE, it needed to be unpredictable and unbiased. And my job as a young mathematician was to show that it really was unbiased to any particular premium bond number. This was quite a skilled and lengthy task to say those weasel words that mathematicians use. We have no reason to suppose that ERNIE is not random.
For me, as a mathematician, complete randomness is fascinating. It's full of curiosities. And unexpectedly, it turns out to have its own rules, patterns, and structure.
This is officially the most boring book in the world, ever. It's called 1 Million Random Digits, and that's literally what it is. Page after page of random numbers. Say what you like about this book, though, at least the plot is unpredictable.
Printed in 1955, these numbers were produced by an early computer rather like ERNIE. And people have used them since for everything from randomized clinical trials to encrypting communications.
I might not read this book cover to cover, but I promise you there's some really interesting parts. I mean, look at this. 0, 0, 0, 0, 0. And here's another great bit. 1, 2, 3, 4, 5. It seems really strange to see these. I mean, how can these be random? But of course, they're as random as the numbers next to them. Not only can you expect to find patterns like these, you can even calculate how often you expect to find them. A perfect sequence of 5 numbers. There should be 50 of these in this book. And the same number 5 times in a row. There should be about 100 of these. You can even expect, somewhere in these 1 million random numbers, the same number to occur 7 times in a row. And I found it. 6666666.
What makes randomness so useful is that it is completely unpredictable, but in a predictable way. So predictable that it has its own shape. A lottery is a great example. Each national lottery draw is, well, random. There seems no pattern at all, but there are also seemingly strange results. Today, after something approaching 2,000 national lottery draws over 20 years, there are huge differences in how often different numbers have come up. Number 38 has been picked 241 times, while number 20 has come up just 171. It might look like something's wrong, but taking all the results together, the totals match the shape of randomness remarkably well. And even the outlying results are just where the shape shows they should be. Here we go. Let's pick some numbers.
It's not a great bet, I admit. There's only a 1 in 14 million chance of me winning the jackpot. In fact, I'm very unlikely to win anything at all. There's only a 1 in 56 chance of me getting the smallest prize of £10. Overall, the lottery only pays back 45% of the money it takes in. Far, far worse than any casino game. If you must play, though you can't change your chances of winning, you can improve your chances of not sharing the jackpot. Many people pick birthdays or other significant dates, so avoid the numbers up to 31. You may even want to steer clear of that supposedly lucky number 38. In the end, it doesn't matter what numbers you choose. Every combination, say 1, 2, 3, 4, 5, 6, is as likely as any other. That's because it's completely random. But randomness can confuse us. For example, use the shuffle feature on the original iPod to play its tracks in random order, and before too long, you're very likely to land on the same album again. People found it so off-putting that the shuffle on later generation iPods was supposedly tweaked. Apple famously explained, "We're making it less random, so it feels more random." Patterns and connections like this are what we call coincidences. And no matter how much we should expect them, they nonetheless still make our heads spin. I love coincidences so much, I decided to try to collect them. Luckily, it's an interest the nation shares.
Well, let's talk about coincidences now at 7:24. Why do they happen?
Professor David Spiegelhalter, good morning.
Good morning.
You are an expert in risk and chance, is what I'm reading here at Cambridge University. But why is it you're interested in chance and coincidence?
Well, it's part of my job. I'm Professor of the Public Understanding of Risk, so everything to do with chance and uncertainty and coincidence is what I'm interested in. And we've set up this website where we're collecting coincidence stories, which people are sending in. And it's sort of things where people, when they happen to them, they say, "Oh, what's the chances of that?" And we're trying to work out what the chances of that really are. It's like a family having 3 children, all with the same birthday, born in different years, but all their 3 children being born on having the same birthday. And you think, wow, what's the chances of that? Well, we can work those out. And it turns out, because there's 1 million families in this country with 3 children, we'd expect there's about 8 families like that. Yeah. Now, we've found 3 of them.
People read great significance, though, into these things. And are they misguided in doing that?
Well, it's Friday the 13th, and this is exactly the day that shows that people do believe in luck and fortune and things like that. So, but I suppose I'm being a bit scientific about them. So some of them we try to just take apart and do the maths of, but other ones are just amazing. There's a lovely example last year where a French family, their house was hit by a meteorite. Whoa, that's pretty surprising itself. But their name was Comet. Isn't that just beautiful?
What are the chances of never experiencing a coincidence, says Steve in Cheshire?
Oh, very low indeed. No. That would be really bizarre.
Good one, Steve.
7:29. What are the chances of any decent weather over the weekend?
Pretty good, actually, Rachel. We've got some clear skies out there at the moment, but because of those clear skies, temperatures are hovering at or just below freezing right now.
The radio show was a huge success. The stories flooded in, over 3,000 of them. We got lots of coincidences with numbers, names and words. And loads of calendar ones, including one more of those rare triple birthdays. Some of these stories are really amazing. Lots of them are about running into friends and acquaintances in the most unlikely places, and I love this one. Mick Preston was on a cycling holiday in the Pyrenees, and during one stopover, he wrote his friend Alan a postcard. But incredibly, on the way to post it, he bumped into Alan, who just by chance was on holiday in the same place. So Mick gave him the postcard in person. As Mick himself said, that was a waste of a good stamp. What's striking is that although these and other coincidences happened a long time ago, people were so jolted by them that they still remember them years later. I think our brains are hardwired to look for cause and effect, to try to come up with reasons why things happen. So when things happen for no apparent reason at all, we find it really spooky. We just don't seem to easily accept that we might not be able to understand or control what happens in our lives. Random events that have no explanation beyond chance saturate our lives. But some people think they can eliminate the random, control everything, and that chance has nothing to do with them at all. Ed Smith was once said to be the golden boy of English cricket. For years, he held an idea about chance, or as he called it, luck, that he shared with many of his fellow sporting professionals.
When I turned full-time professional in 1999, we had all these meetings about how we were going to approach the season. And someone put his hand up and said, I don't think we should say bad luck to each other. That's an excuse. It's not bad luck. If someone gets out, it's their fault. I think as sportsmen, we're conditioned to think that you are in total control. I mean, if you walk out to bat in professional cricket and you say, well, maybe I'll be lucky and maybe I won't, and maybe someone will bowl a good ball and I'll be out and I can't do anything about it, then you're stacking the deck against yourself before you even begin.
Ed played for England and became captain of Middlesex. Everything went well for him until one day during a county cricket match at Lord's.
So we're in the middle of this match, it's going well, we're pretty much cantering to victory, we're on a bit of a streak of 5-6 wins in a row, everything's going well, and I'm doing the most routine thing in cricket. I'm running a 2, it happens all the time, you know, it's not particularly demanding athletically to run 20 yards and then come back again. And I ran the first one, and then you just run the bat in. And I just sort of collapsed. And I'm lying in this, I had this shooting pain in my ankle. And it was only quite a few weeks later that there was an X-ray, and it turned out that I'd broken my ankle, and I wasn't going to play anytime soon. I missed the rest of that season, and then I retired effectively at the end of that season, and didn't play professional cricket again.
In a single moment, Ed's entire career vanished. He had been touched by chance. No one and nothing was to blame.
I think I found it hard to accept, you know, my own willpower, my determination to control, to shape my own life was so great. But the reality is that I wasn't in control of the fact that I had a broken ankle. It was just a fact. It was a circumstance that had happened to me. So it was like a clash between my own desire to control everything and the fact of luck, and, you know, luck won.
The moral of Ed's story is clear. Don't beat yourself up about every failure. But the opposite is also true. Don't be too chuffed with yourself about every success. Remember this? I know you can't get rid of luck, but right now, I wish you could. The parachute hasn't failed, at least. I don't seem to be being blown into a forest. And I haven't even been sick.
That was so cool. Can we do it again?
You know, the really interesting thing is that whilst I was confident I would land safely, I couldn't be absolutely certain. The question is, why not? Why does chance exist? The story of science for centuries has been a triumph, unlocking the mathematical laws behind everything from the atom to the universe. So why is there still room for the random, for unpredictability? Why instead can't everything in nature be determined? In which case, we could get rid of chance altogether, and I would be out of a job. In the 1680s, Isaac Newton revolutionized science with a set of universal laws. He calculated the orbits of moons and planets, even predicted the timings of eclipses, and of course explained the fall of an earthbound apple. Newton's friend Edmund Halley predicted the returns of comets. And other scientists eagerly worked to discover new laws and make more predictions. The Enlightenment, it came to be called. In 1779, the French scientist Pierre-Simon Laplace had a bold vision. If some vast intellect could not only comprehend all the laws of nature, but could also measure everything, even down to the tiniest atom, then he might predict the future precisely, and uncertainty would simply disappear. In theory, with the right mathematics, everything in the physical universe could be measured and predicted, just like the movement of the stars and the planets. So, for example, if I threw a dice, I could predict exactly how it would land. This theory is what we call scientific determinism. In theory, if we gather the data and do the calculations, we should be able to get rid of chance altogether. But in practice, prediction has proved frustratingly hard. It's as if there's something about our physical world that makes prediction all but impossible. Despite the promise of the laws of Newton and all the scientists who followed him, we remain in the dark. But why? In the 20th century, scientists, like meteorologist Ed Lorenz, discovered that even tiny influences could have immense and unpredictable consequences. As Lorenz put it, the flap of a butterfly's wings in Brazil could cause a tornado in Texas. The theory of determinism had to acknowledge complexity and chaos. The laws of physics weren't wrong, but the real world was just too complicated to ever fully comprehend. Also in the 20th century, physicists like Werner Heisenberg, delving ever deeper into the nature of matter, realized there was an absolute limit to what they could ever know. In his work on quantum mechanics, Heisenberg set out the uncertainty principle. Essential parts of the subatomic world could at best only ever be described as a probability. The dreams scientists once had of conquering chance have been shattered. Quantum mechanics has shown us a subatomic world that is fundamentally uncertain. Beyond the subatomic, we are still governed by mechanical and therefore deterministic laws. But paradoxically, the mathematics of chaos and complexity means that things are still ultimately unpredictable. So what is chance? Is it real? Is it something out there in the fabric of the universe? Or is chance in here just an excuse, what Laplace called merely the measure of our ignorance? Or is it a bit of both? After centuries of discovery, we're still not much closer to knowing what chance really is. One thing is certain, chance is here to stay. And what's more, it's actually been put to work. Faced with complex and unpredictable problems, scientists have found ways to use chance itself to convert blind uncertainty into computable probability. In the early years of the Cold War, nuclear physicists at Los Alamos were working to design a new atomic bomb. They wanted to predict when an atomic chain reaction might go critical, but the physics was so complex that at each step in the chain, they were uncertain about what would happen next. So they turned to the mathematics of chance. For each step, they chose an outcome at random and then calculated what the resulting chain reaction would do. Then they randomly chose a new set of outcomes and calculated a new result. They did this repeatedly until they had hundreds of different but equally likely possible results. And combining them all gave the Los Alamos scientists an extremely accurate probability for what the chain reaction would do for real. They called it the Monte Carlo method, like rolling a dice over and over again. And the bomb worked. Today, that very same Monte Carlo method, creating arrays of possible futures to compute probabilities, is being used to try to solve problems in many different fields. And what's most exciting for me and my fellow Brits is that this might help to answer that all-important question, when I go out, do I take an umbrella? In the 1920s, the economist John Maynard Keynes wrote a famous book about chance. And for the ultimate metaphor of impenetrable uncertainty, he chose the British weather. He wrote, "Is our expectation of rain when we start out for a walk always more likely than not, or less likely than not, or as likely as not? I am prepared to argue that on some occasions none of these alternatives hold, and that it will be an arbitrary matter to decide for or against the umbrella." But we want certainty, and so we demand it from our weather forecasters. And then after wet weekends and washed out holidays, we blame the poor old forecasters for getting it wrong.
Hello to you. Well, it was a very disappointing day today in many places. I'm optimistic that it's going to be a better day for most of us through tomorrow.
Britain's most famously wrong weather forecast was on the 15th of October 1987.
Good afternoon to you. Earlier on today, apparently a woman rang the BBC and said she heard that there was a hurricane on the way. Well, if you're watching, don't worry, there isn't.
But there was! That night, England was lashed by the strongest winds for almost 300 years.
Southern England suffered the full fury of the freak hurricane-force winds. In their wake, a trail of devastation, the worst damage to property since the Second World War. Nowhere escaped unscathed.
Today, the most advanced meteorologists don't try making predictions like Michael Fish did. In Reading, at the European Centre for Medium-Range Weather Forecasts, they use a form of Monte Carlo method to make forecasts using probabilities instead. To show why they do this, they've revisited the same weather data Michael Fish had in 1987.
What this shows us is that October 87 was an exceptionally unpredictable and exceptionally chaotic situation. And so it was always going to be impossible to make a precise deterministic forecast.
Weather forecasts go wrong because even small errors at the beginning can grow into huge differences after just a few days. And that's as true for everyday weather as it is for hurricanes. To tackle the problem, Tim Palmer and his colleagues routinely compute 50 different forecasts, each with slightly varying starting points to reflect the uncertainty. Before returning to the hurricane, Tim shows us an everyday example.
So we're looking at today's weather forecast, pretty much right at the beginning of the forecast period. These are all basically giving the same type of weather. So a weather forecast would look at these pressure maps and say, okay, there's a northwesterly airstream coming down over the UK. It's giving us slightly cool temperatures, but fundamentally it's exactly the same no matter which of these 50 forecasts you're looking at.
Taking the same set of forecasts to 3 days in the future, it's a different story.
Now there are discernible differences. For example, member 14 has a stronger wind. There are tighter gradients in the pressure than, say, member 15. And that's telling us that although the general direction of the wind we can be certain about, it's coming from the northwest, the strength of the wind we cannot be so certain about. So we have to make a prediction in probabilistic terms.
To work out the probabilities, Tim counts how many of the 3-day forecasts show a particular kind of weather.
It turns out that in about 30% of the forecasts there are gale force winds over much of England. Similarly, rainfall, we find across much of England about 30%. What this doesn't mean is that it's raining for 30% of the day. What it means is that over the 50 possible futures, in 30% of them, it is raining.
So what can Tim see using the new method with the 1987 hurricane data?
There's around a 20 to 30% probability over parts of southern England of hurricane-force winds. Now, the probability normally of hurricane-force winds in southern England is negligibly small. So even though there's a divergence of solutions, there's real information here.
Adapting the Monte Carlo method and embracing chance gives much better results. But in Britain, the forecasts most of us see don't give us this kind of information. Yet,
we really should now be trying to get this type of information out on the daily weather forecast. And indeed, I think it will enhance the credibility of meteorologists themselves to be able to say Not only is weather forecasting an uncertain science, but we can actually quantify the uncertainty in a very precise way.
If you were a cynic, you might think that weather forecasters who give you probabilities and not predictions are just hedging their bets, ducking out of doing the one thing they're supposed to so they can never be accused of being wrong again. But I don't agree. Better a reliable probability than a wrong prediction. And knowing the probabilities, we can all make our own decisions. Like to bring that umbrella.
Remember that San Francisco probability? A 40 to 80% chance of an earthquake? In 1906, the city's worst ever earthquake killed 3,000 people and destroyed almost 30,000 buildings. Even if a similar catastrophe in the future can't be predicted, it certainly can't be ignored. So today's scientists are applying new mathematical methods to the problem. They're computing probabilities literally building by building, so bold decisions can be taken about what to do. In Berkeley, across the bay from San Francisco, one major fault runs right across the pitch of the California Memorial Stadium, home of the Golden Bears football team. They're rebuilding the stadium at a cost of over $200 million.
The fault starts just to the west of the south scoreboard, and you can see in the bowl there are those double stair-step curves
Right.
at 2 points. That's where our joints are for that piece of the stadium.
Right.
And it allows this part of the building to move independently in an earthquake from the two sides of the stadium on either side of it. And the base of the entire part of that building is on layers of sand and high-density polyethylene plastic.
That's amazing.
Which allows that part of the building to move a little easier than it would otherwise.
Right.
So when the ground moves 6 feet horizontal and 2 feet vertical, it can just go along for the ride.
Okay.
And the rest of the stadium is protected.
The stadium is just one part of a massive building and strengthening program all around San Francisco Bay. A colossal $30 billion has been committed in total. Will it be enough? They can only hope so.
Even if we knew exactly what earthquake is going to occur, we may not know exactly how strong the shaking will be and how it'll vary across the city because of different soil types. So you set a standard, you agree the buildings will be built to that, and then you hope that that's good enough. You can't actually engineer chance out of the system altogether.
At least in San Francisco, they've a good idea of what to expect, even if they can't know exactly. But there's one last sting in the tail. Chance can sometimes come up with something you never even thought of.
As we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns, the ones we don't know we don't know. And if one looks throughout the history of our country and other free countries, it is the latter category that tend to be the difficult ones.
Donald Rumsfeld may have just been trying to excuse an unfolding disaster in Iraq. But unknown unknowns are a real and profound challenge for us all. And don't we just know it? The Bank of England is the rock-solid institution to which we all turn in these turbulent times. Surely I can find some certainty here. I'm meeting Spencer Dale.
The Bank of England is the main financial institution in the country. People look to it to tell them what's going on in the economy. Can you predict what's going to happen?
Unfortunately not. Forecasting the economy is a very difficult thing to do, in part because the economy is very large and complex. And it's made even more difficult because it depends on people and their decisions. And that makes trying to model behaviour and how the economy is going to change over time even more difficult.
Every quarter, the bank makes a forecast for the nation in the form of what it calls a fan chart, and it deliberately builds in uncertainty. The chart shows that Britain's future economic growth might have a 5% chance of lying in each one of the shaded bands. This was the bank's chart from 2007, just before the big crash.
At the time we made this forecast, we thought in 3 years' time, the annual growth of the economy may be anywhere between 5% or close to zero.
But the bank is even less certain than that. It also leaves room for the unknown unknowns.
This only shows the 90% of probabilities. So it shows you 90 times out of 100 we think the economy will go somewhere in this range.
So there's a 1 in 10 chance it could just do anything?
There's a 1 in 10 chance it will fall outside of this fan chart. We don't try and put precise probabilities on those very extreme outcomes.
With these charts, the bank is making one thing clear. We must expect the unexpected. And soon after the bank made this chart, chance struck.
It was a genuinely surprising event. The economy behaved in a way which we hadn't seen for almost an entire generation. The environment in which we operate in is inherently uncertain, the future is uncertain, and the impact of our decisions are often very uncertain.
Some people might want to hammer the Bank of England for not knowing what's around the corner, but you can't blame them for the nature of chance. And though the bank can't give us the information we want, I think they show the way to the wisdom we need. There's just no use in looking for absolute certainty. We can never rely on predictions. We can tame chance, but only up to a point.
Putting numbers on chance is a powerful way to get a handle on the future. But these numbers can only ever be as good as the information we have to hand. Though we try to measure reality with precision, sometimes they're little more than guesses. What all this means is that uncertainty is an essential part of being alive. And whether our uncertainty ultimately comes from out there or in here won't in the end matter, because either way, surprises will most certainly happen. For instance, in this year of the Diamond Jubilee, I found a chicken nugget in the shape of Her Majesty the Queen. What's the chances of that?